Okay, we're returning to our old friend, the binomial distribution. So this particular Desmos page lets me look at the binomial distribution for a set value of n. In this case, I've got 6, and a p-value, I've got 0.12, and it shows the probability of each outcome. So the maximum possible outcome that I can get is 6, which is actually 0, 1, 2, 3, 4, 5, 6. So you can just see a minute blob there. There is a probability at 0 which ends here. That's the most common outcome. Then there's a gap because the binomial distribution, of course, is discrete. So I can only get whole number outcomes. So after 0, the next probability is at 1, which is this stick here. So it's just under 0.4. And you could check all those probabilities on your calculator. So this is a way of illustrating the binomial distribution and watching how it changes when I muck around with the values of n and p. So I can make n smaller. Okay, so this is n equals 1, so the only two outcomes are 0 and 1. 0's got a very high probability. Okay, I can increase the values of n. Now, as I increase the values of n, and as I change p a little bit, then for this value of n and p, I've got n is 41, p is 0.45, and this distribution looks suspiciously close to the normal distribution. In fact, I can ask this page to put the normal distribution on top of that, and if I do, what it will try and do is draw a normal distribution, and it sees, you can see it makes an astonishingly good fit. So this is not a coincidence. You can prove this mathematically, though I'm not going to. If for some values of n and p, all right, the normal distribution is a very, very good fit to the binomial distribution. So our first task is to figure out what kind of values of n and p were good. Well, my first one, when n was 6 and p was 0.18 or something, was about like that. You can see the normal distribution. The red curve is doing a really pretty poor job of fitting the sticks, and there are very, very few sticks anyway. In fact, for any small value of n, less than about 20, the binomial distribution is just going to have only a few sticks in it, and the red curve is going to have a hard job to actually do that justice. So for large values of n, we really mean above about 20 or something. But you can see this particular value of n, although n is big, this particular one isn't working very, very well either. I mean, this normal approximation seems to think that negative values are possible. So as well as making n big, it really helps if p is not too close to 0, because then we get a bad match. It's also bad if p is really close to 1. I get something very similar happening there. Okay, just not very many bars. If I take off the normal curve thingy, then you can see that no way that would remind you of a normal distribution. So the right sort of value for p is somewhere in the middle. Okay, so when p is around a half and n is more than about 20, okay, then we get a good approximation. Okay, the bigger I make n, okay, the more I can maybe make p a little bit closer to 0, and the normal approximation, put it on, drag this up. Well, not brilliant, but it's not too bad. If I make n bigger, leaving p as a small value, n's now 100, and p equals 0.1, the approximation is not too bad. Okay, if I make p a little bit bigger than that, like 0.15, the approximation now is looking really rather good. Okay, so we need to first of all decide when this approximation seems to make sense. And we've said that values of n, the bigger the better, and values of p, the closer to 0.5, the better. So if I make it 0.5 for n is 100, then if I can actually move the window so you can see it, it's a very, very good fit to the normal model. Okay, so if we now have a look at your notes, you can see that you've got this rule. Okay, np and n times 1 minus p both being close to 10. Okay, this actually, if you can see, if you think that n is big and p is close to a half, then if n is 20, which is about the smallest value that counts as big, and p is exactly a half, then np is just going to make it. It's going to be 10. And n times 1 minus p, 1 minus a half is also a half. That will also be a 10. So e.g., okay, n equals 20 and p equals a half. That just about qualifies for n big enough and p close enough to a half. The bigger n is, the more p doesn't need to be close to a half. So our test is np and n times 1 minus p must both be at least 10. So we're going to be using that. Okay, but there's another big issue with using this approximation. So if we go back to the this picture, let's move my window. Okay, and let's bring n down a little bit so you can see the whole curve. There's still a big difference between the normal curve and these sticks for the binomial. And it comes back to what we said very near the beginning: binomial is discrete. So this probability here, it looks like that's for the outcome 33. 33 has got a probability all on its own, but because it's only whole numbers, 32.5, 32.7 all have 0 probability. So the probability comes in a chunk. Now that's not the way things work with the normal distribution. The normal distribution, the probability of any different individual outcome is 0, and we get the probability by looking at the area of some kind of strip underneath the normal. So we need to find a way of turning these sticks, which as far as the normal curve is concerned have no probability because they have no area, into something that has an area. And the easiest way to do that is to turn each stick, so this one here, into a rectangle. So moving this slider here puts the rectangles on. So the strip, if this value here, which would be 32, I've still got the line there, but now it's at the center of a rectangle. So the area of this, now this rectangle will go from 31.5 to 32.5. Those are the values that would round to 32 if I allow values that aren't whole numbers. So as part of the process of approximating a binomial by a normal is we have to let the binomial probabilities spread out on either side so that the value 32 begins to own all the values between 31.5 and 32.5. Okay, so if you've got that general idea that we need to let binomial single number outcomes spread by 0.5 on either side, then you'll be okay. When we come to do an example, I'll show you how this works. It's called the continuity correction, and there's a really easy way of setting it up as long as you draw the diagrams that I've asked you to in the past. So let's go back to our booklet. Okay, our first example for a normal approximation to a binomial. Okay, all right, we're kind of going to do this in dotting around, I think, because the first thing is that the binomial we're given, okay, n is 60 and p is 0.2. I'm going to answer part D first. Okay, I'm going to look at np and I'm going to look at n1 minus p, and the test is that these both have to be at least 10. So np for the binomial is 60 times 0.2, which is 12. Hooray, that's more than 10, so that is greater than 10, I state that here. And at 1 minus p is going to be even better. I'm going to get 60. 1 minus 0.2 is 0.8, so 60 times 0.8 is 48, which is also greater than 10. So I state these are both greater than 10, so the normal approximation is valid. Okay, the bigger n is, the closer p is to a half, the more that these two do beat the value of 10, the better. But this is good enough, they're bigger than 10, so that's valid. Good. All right, now let's flip back. Okay, we've talked a lot about a normal approximation being able to be set up, but we've never actually set one up yet. How do we get a normal distribution that is the closest match we can make to the binomial? Well, the things that we can work out from a binomial is we can work out the mean for a binomial, and we can work out the variance for a binomial. These are formulas we've used before. We've also got the square root of the variance giving the standard deviation. And if you remember, what I need for a normal distribution are the mean and the variance, sigma squared, or I could just specify sigma. So I need to set up a mu and a sigma squared, or a sigma, for my distribution. So in part A, I know it's going to be normal, but I need to set up my parameters. Mu is, for the binomial, it's np, which I've already worked out over here. It was 12. Okay, and my sigma squared, I haven't worked out yet, is np 1 minus p. I've already done np, which is 12, times 1 minus p is 0.8, because p is 0.2. And 12 times 0.8 is, what, 9.6? Okay. And when I set up sigma squared, it's such a good idea to work out sigma 2. So I square root my variance sigma squared, and I get my answer here. There it is in its most useful form. So 3.098. Now, although I've got that as a decimal, actually, I'm probably going to be able to get away with typing in root 9.6 as long as I don't forget the root. So I might put this bit in brackets. Okay, have I done what it said? It said state a distribution, which can be used to approximate x. So I haven't quite done that. I've got a mean and a standard deviation. But the point was to state what x approximately twiddles, which is a normal distribution, okay, with mean 12 we've seen, and variance 9.6, not 9.6 squared. Okay, this is the sigma squared value. Sigma equals the square root of 9.6. I'm going to write down there. So this is specifying an approximate distribution for x. Good. Okay, now we've got to do continuity corrections. So in part B, okay, I think I want the probability that x is less than 8. Now, it's a binomial, or at least starts as a binomial, so you'd draw this diagram, wouldn't you? Okay, and you'd put ticks on the ones you want. So I want 7, I want 0, I don't want 8, I don't want 9, and you do your inclusion and exclusion boxes. Well, in this case, I just need an inclusion box. Okay, so for a binomial, you'd now go on your calculator and you work out the probability of being less than or equal to 7. But remember, we're going from a discrete binomial to a normal. So therefore, the gap between 7 and 8 now exists, and we have to let 7 spread out to fill that gap. Okay, so therefore the probability I'm going to work out, the continuity corrected probability, is going to be the probability that x is less than, and this value that I'm going to take as the cutoff isn't 7, it isn't 8, it's in the middle. So when you draw the diagram, where the box comes between two numbers, you just use the whatever 0.5 value it is. So this is x is less than 7.5. Or I could just as equally well write x is less than or equal to 7.5. Okay, now we're on a normal, which is continuous. The probability of equaling 7.5, okay, doesn't matter. Okay, while we're on the binomial, then being up to 7 is very different from being up to and including the 8. The 7 and the 8 have a definite probability. But when we go to the normal and we're on the 0.5s, it doesn't matter whether we say greater than or equal to, sorry, less than or equal to, or less than. So this is the approximation that I've got to use for the normal, and we call this the continuity correction for this original probability. That's relevant to the exact distribution. This is only relevant to the normal approximation. So for the remaining bits of B, for part 2 of B, okay, I've got to do the probability of x being less than or equal to 10. So draw the diagram, 0, 9, 10, 11, ... less than or equal to 10, so it can be 10, it can be 9, it can be 0, it can't be 11. Box would come like this for my inclusion. There's no exclusion box. So therefore, my cutoff value is 10.5, and I'd just do the probability of x being less than 10.5. Or less than or equal to 10.5, probability of being exactly 10.5 on a normal is 0. So I'm going to leave it like this time. Yeah, okay. So the next one, part 3, okay, was x being, what was it? X being greater than 12. If it's greater than 12, okay, I can have 13, but I can't have 12 or 11 or 0. So my inclusion and exclusion boxes, well, one box would just include everything, okay. The other box would be the exclusion box here, which would come between 12 and 13. Now for a binomial, I'd do the big box minus the small one. For the normal distribution, all I need to take into account of is this cutoff value, the probability of being one side of 12.5, because it's between 12 and 13. But on a normal distribution, I'm going to do that by saying x is greater than 12.5, or greater than or equal to, if you prefer. Okay. All right. Of course, we're going to work out the normal probabilities later. We're just doing continuity corrections for now. So x greater than 12 becomes x greater than 12.5, and the final one, which was x greater than or equal to 6, but less than 9. So for the last one, probability of x being greater than or equal to 6, so this is the initial probability, x between 6 and 9, but with those kinds of inequality signs. That's the exact probability, but for the continuity correction I need to do the diagram. There we go. So I want 6. I'm allowed to have 6, but I'm not allowed to have 0 to 5. I'm allowed to have 7. I'm allowed to have 8. I'm not allowed to have 9, so that's a cross. I'm not allowed to have anything else this going this way either. So my inclusion box would become like that, and my exclusion box gets rid of all the crosses like that. So my limits are 5.5 and 8.5. So my continuity corrected probability would be 5.5 is less than x is less than 8.5. Once again, these could have equals on them. It would make no difference because the probability of equaling 5.5 or 8.5 for a normal is 0. Okay? So for the exact one, you can't tinker with these because that would affect which numbers get ticks in which box, because this one is still talking about discrete, but when it's talking about continuous, you can actually use strict or weak inequality signs, and either is okay. Right, now all I've got to do is work out the corresponding probabilities. Now I've corrected C, it should be corrected in your booklet. All C is asking you to do is work out the probabilities that we've set up the continuity corrections for. So the probabilities mentioned in C are still talking about the binomial being less than 8, but I now know that for a continuity corrected normal approximation, I'd need to change that into x being less than or equal to 7.5. So for part C1, I need to start with a normal, and it's the normal I had in part A, this one here, and I need to work out this probability. Okay, so I've set up everything I need. So I've gone for some more space here on a separate piece of paper. Hopefully you'll be able to manage in your notes. So I'm working with this normal distribution, this probability, this exact binomial probability I'm forgetting about. I'm working about the continuity corrected normal probability. So it's a normal, so now I need the diagram for a normal. Okay, the previous diagram was just for getting the continuity correction. I want x to be less than 7.5. I've got a normal distribution. The mean of this is at 12. Okay, so 7.5 is going to be definitely this way. Okay, z's naught here, so this will be a negative z. My z formula, okay, forwards normal distribution question, because we're finding a probability. Okay, so I'm going to be doing something minus the mean divided by the standard deviation. The mean is 12. Okay, the standard deviation is not 9.6, it's root 9.6. And the value I'm standardizing is 7.5. So I work out z on my calculator. I'm not forgetting that all-important square root, and I get a z value of minus, I thought it was going to be minus, z equals minus 1.452. Okay, now what do I do? Well, I've got to find the probability. I haven't shaded my diagram yet. I want this one here. So I'm going to be using this z value here as my upper limit, and my lower limit is going to be minus 9999. So now I go into my normal distribution, normal CD, note 2, and my lower limit is minus 9999, and my upper limit is minus 1.452. So my probability is, my p-value is 0.07325. Okay, so this is now the kind of thing that you've learned how to do from normal distribution, and really you should be able to now take all the work we've done, so that work we did in part B where we set up all the continuity corrections, we've got a normal distribution. You should be able to turn all of these probabilities into well, get z values for them. This will have a lower and an upper limit. Do sketches and you should be able to get all the answers for the probabilities. So pause the video, get them, and then just use the rest of the video as a check. So see part 2, the original probability in the question is less than or equal to 10, but the continuity correction says that I should do less than 10.5. We did that in part B. I need my sketch. It looks very similar to the one before because again I'm below the mean and I want a value less than that. So the z calculation is going to look similar. There it is, and my z value is minus 0.484. Once again, I want the probability to the left of that, so I'm going to be using a lower of minus 9999, but I just need to update my upper to this new value. And here comes my probability of 0.31415. Double underline it because it's an answer, move on to the next part. The next probability asked for is x greater than 12, but I've already transformed that into the continuity correction. X has got to be greater than 12.5. So I can say goodbye to this. Okay, this is the one that I'm using the normal distribution for. So I do my diagram. 12.5 is above 12, and I want to be bigger than 12.5. Z calculation is very similar to the previous two. Here it is, and my calculator tells me the answer to that is that. There it is, and I'm going to be using that as my upper, as my lower this time, and my upper is going to be 9999, so put that value in as the lower, 37, and change my upper to 9999. Okay, I'm clearly expecting a probability of less than a half, which is just as well, because that's what I get. I get 0.4359, double underline it, that's my answer. One more to do, see part 4. Okay, the question asks for probability from being greater than or equal to 6 up to but not including 9, but I've already done the continuity correction, so I forget all about this. I use my normal distribution for this, and I do the diagram. So my diagram looks like this. 5.5 and 8.5 are both less than the mean of 12. I want the area between them. Two z values using similar formulas. Here are the calculations you should see and the values you should get, and I can see that I want the area between those two, so I'm going to use the more negative one as the lower, the other one as the upper. There they are on my calculator. I've rounded them off to 3 decimal places, and here comes the probability. There we go. Here's my last answer. So we've covered a lot of ground in that video. Hopefully the last 5 or 10 minutes you did all of those questions yourself, and you've now just checked you got the right answers. Do make sure you're setting out your solutions in full with the diagrams. There may not be enough space in the booklet. Sorry about that.